Welcome to this specialized mathematics lecture on heights and distances, designed for Class 10 students. Today, we step out of abstract algebra and right triangle proofs and into the real physical world. Heights and distances represent the primary and most powerful applications of trigonometry. Historically, before satellites and GPS existed, ancient surveyors, navigators, and astronomers used these exact trigonometric ratios to map entire continents, measure the heights of active volcanoes, navigate vast oceans, and calculate the exact distance from the Earth to the Moon. Today, heights and distances principles are the foundational science powering GPS mapping, modern civil engineering, architectural design, forestry, and military trajectory calculations. When architects design skyscrapers, or surveyors map out new bridges, they use angles of elevation and depression to calculate heights and distances without ever using a physical measuring tape. Let us embark on this practical journey and master these real-world trigonometric applications together. To solve heights and distances problems, we must first establish a precise geometric coordinate system. Imagine an observer at a specific viewpoint looking at a target object. The line drawn directly from the observer's eye to the target object is called the line of sight. Now, draw a straight horizontal line starting from the observer's eye. This is called the horizontal level. Together, the horizontal level and the line of sight define the basic visual coordinates. If the target object is located higher than the observer's eye, the observer must look upwards. This forms the angle of elevation. If the target object is located lower than the observer's eye, the observer must look downwards, forming the angle of depression. Understanding these two simple lines, the line of sight and the horizontal reference level, is the key to unlocking all heights and distances word problems and constructing accurate right-angled triangles. Let us examine the angle of elevation in detail. The angle of elevation of an object viewed is the angle formed by the line of sight with the horizontal level when the object is located above the horizontal level. In other words, it is the angle you must lift your eyes to look at something tall, like the top of a tree, a flying kite, a bird on a branch, or a hot air balloon floating in the clouds. Geometrically, this elevation angle, along with the vertical height of the object and the horizontal distance to the object, forms a perfect right-angled triangle. By using trigonometric ratios, especially the tangent ratio which links the vertical opposite height and the horizontal adjacent distance, we can calculate the exact height of extremely tall structures without ever having to climb them or drop a physical plumb line. This simple elevation relationship is the base of building construction and aviation navigation. Now let us examine the opposite case, the angle of depression. The angle of depression of an object viewed is the angle formed by the line of sight with the horizontal level when the object is located below the horizontal level. This occurs when an observer stands at an elevated height, like the top of a lighthouse, a balcony, a cliffside, or an airplane cockpit, and looks downwards at a target on the ground or water, like a car on a road or a ship at sea. It is critical to note that the angle of depression is measured from the elevated horizontal reference line, not from the vertical wall. Geometrically, the elevated horizontal level is parallel to the ground or sea level. Therefore, by the alternate interior angles theorem of geometry, the angle of depression from the top observer is mathematically identical to the angle of elevation of the top observer when viewed from the ground object. This simple geometric equivalence translates depression angles directly into simple ground-based right triangles. In Class 10 heights and distances problems, we restrict ourselves to the standard angles of 30 degrees, 45 degrees, and 60 degrees. This is because these angles yield clean, exact trigonometric values that are easy to calculate. Let us review the standard tangent values, which are the primary ratios used in these problems. The tangent of 30 degrees is 1 over the square root of 3, or approximately 0.577. This is used for shallow elevation angles where the horizontal distance is larger than the height. The tangent of 45 degrees is exactly 1. This is the most elegant case, representing an isosceles right triangle where the vertical height and the horizontal distance are perfectly equal in length. The tangent of 60 degrees is exactly the square root of 3, or approximately 1.732. representing a steep elevation angle where the height is larger than the horizontal base distance. Keeping these values memorized is essential. Let us solve a practical single triangle word problem step by step. Imagine a surveyor standing 30 meters away from the base of a high tower. Looking up at the top of the tower, the surveyor measures the angle of elevation as exactly 30 degrees. Let us calculate the height of the tower. First, we sketch the right-angled triangle ABC. The base AB represents the horizontal distance of 30 meters. The vertical side BC represents the unknown tower height H. The angle at vertex A is 30 degrees. Since we know the adjacent side and want to find the opposite side, we apply the tangent ratio. Tangent of 30 degrees equals opposite over adjacent, which is h over 30. Substituting our standard value, 1 over square root of 3 equals h over 30. Multiplying both sides by 30, we get h equals 30 over square root of 3. Multiplying numerator and denominator by square root of 3 to rationalize, it yields exactly 10 square root of 3 meters, or approximately 17.32 meters. More complex physical applications involve 2 right-angled triangles instead of 1. These double triangle problems typically occur in real-world scenarios where an observer measures angles to 2 separate objects, or when an observer measures the top and bottom of a structure from an elevated tower, or when a flagstaff is mounted on top of a building. Geometrically, the key to solving double triangle problems is to split the drawing into 2 distinct right-angled triangles that share a common side, either a common vertical height or a common horizontal base distance. By setting up 2 separate trigonometric equations, we can substitute the common variable from one equation into the other, algebraically resolving the system to find unknown heights and distances. Let us look at the Lighthouse ship scenario as a master example of this dual triangle system. Let us solve a double triangle problem step by step. An observer stands at the top of a 75-meter-high lighthouse. Looking out at the sea, the observer notices 2 ships directly in line with the lighthouse on the same side. The angles of depression of the ships are 45 degrees and 30 degrees. Let us find the distance between the 2 ships. First, we sketch the drawing. The lighthouse AB has height 75 meters. The ships are at C and D. By alternate interior angles, the angle of elevation at the closer ship C is 45 degrees, and at ship D is 30 degrees. Let distance BC be x, and the distance between ships CD be y. In triangle ABC, tangent of 45 degrees equals 75 over x. Since tangent 45 is 1, x equals 75 meters. In triangle ABD, tangent of 30 degrees equals 75 over x plus y. Substituting x equals 75 and tangent 30 as 1 over square root of 3, we cross-multiply to get 75 plus y equals 75 square root of 3. Solving for y, we get 75 times the quantity square root of 3 minus 1 meters, or approximately 54.9 meters. Let us examine another powerful double triangle case, observing a building from a high tower. Suppose from the top of a 75-meter-high cliff, an observer measures the angle of depression of the top and bottom of a vertical tower as 30 degrees and 60 degrees respectively. Let us calculate the height of the tower. First, we sketch the system. The cliff AB has height 75. The tower CD has unknown height H. Draw a horizontal line from the top of the tower meeting the cliff at point E. This splits the drawing into 2 right triangles sharing a common horizontal width. The larger triangle gives us the width. Tangent 60 degrees equals 75 over width. So width equals 75 over square root of 3, which is 25 square root of 3 meters. The smaller triangle gives us the height offset. Tangent 30 degrees equals the offset over width. So offset equals width times tangent 30, which is 25 square root of 3 times 1 over square root of 3, which simplifies to exactly 25 meters. The tower height is the cliff height minus this offset. 75 minus 25 equals exactly 50 meters. Let us consolidate our heights and distances knowledge on our academic summary dashboard. We began by establishing the core line of sight and horizontal reference levels. We define the angle of elevation as looking upwards to an object above the horizontal level, and the angle of depression as looking downwards to an object below. We verified the alternate interior angle equivalency that links depression angles directly to ground-based elevation right triangles. We reviewed the standard tangent values. Tangent 30 is 1 over square root of 3, tangent 45 is exactly 1, and tangent 60 is square root of 3. Finally, we mastered problem-solving strategies, successfully applying single right triangle geometry to tower heights and double right triangle systems to calculate ship distances and tower height offsets. These algebraic and geometric templates connect seamlessly, showing how simple triangle ratios structure physical measurements in our modern world. Thank you for attending this comprehensive mathematics lecture on Unit 5, Heights and Distances. We hope this visual geometric journey has given you a profound understanding of angles of elevation, angles of depression, alternate interior equivalents, and step-by-step single and double right triangle problem-solving templates. If you found this video helpful, please consider supporting our educational mission by liking, subscribing, and sharing this channel with your fellow classmates. Leave a comment below if you have any questions about alternate interior angle mappings, standard tangent value rationalizations, or multi-triangle exam problems. Stay tuned for our next academic lecture, where we will transition to our next unit chapter in Class 10 Mathematics. Keep exploring the beauty of geometry and algebra, and we will see you in the next lecture.